Welcome to Whitening Lactose Sustainably. Before we start with this how to whitening lactose in an eco-friendly and cost-effective way, I would like to thank you everybody for joining and good morning to everybody. Before we get started, I'd like to walk through a few housekeeping items. This presentation is being recorded, so we can send you a recap afterwards. Your camera and audio will be turned off. However, you can chat and you can make questions, Q&As. For instance, they are enabled for you to submit questions and comments. I'll answer all your questions after the presentation, and I'll follow up with the groups of those who are not able to reach out to. So let's get started. My name is Michael Christensen. I am based in Søborg in Copenhagen, Denmark. I'm the Technical Sales Director of Copenhagen in Denmark, and I'm the specialist within drying and evaporation. And my background is in process design, commissioning, and plant operations. I'm working with external and internal stakeholders to identify the right size of opportunities, ranging from very small scale plants up to full-scale drying and evaporation systems within various applications. So let's move to the agenda of today, where we'll be talking about the blue light whitening system. The blue light whitening system is actually a product that is utilized in the side stream from producing cheese, that is whey. And the whey is then utilized in various applications within the dairy industry. So you can see here, this small flower, a lot of different applications is where whey can be produced or used as a produced product. One of them is lactose, and the end application for lactose is what you can see here in the left-hand side, ranging from infant formula into bakery, dairy, beer, and even marinations where lactose is utilized. So a huge variety of application is where lactose is utilized in the industry. The industry likes to have the lactose as white as possible. In some cases below 2 ppm, and so that's part per million. So a very low degree of remaining vapor in the end crystals. And it is again a goal, to get to the lowest possible content of vapor. Today's traditional way of removing that is in the high-yield process that is patented by Anhydro SPX, where we have the beverage part of the system here, and we have the calcification system here. We have the decoloring system here. We have some intermediate tanks going to an evaporator system, crystallization tanks, sieving of the secondary, and then into the fluid beds where you're drying the crystals coming in into the powder, which is then ending up in the silo and then into bags of the bags of it. Trick here today is that today is utilized active carbon, and this active carbon is consuming and withholding the amount of vapor within its very big surface area. There's a backside to this, and flip side to this. It needs to be regenerated. So it's actually a duplex system, and you see one tank, one pump. It's actually a duplex system. So there are two tanks, one in operation, where it's actually trying to contain the vapor, and the other one is in regeneration mode. So this is where it is being cleaned. So in this cleaning process, it is utilizing, in average, 250 cubic meter of water per day, and also the cleaning agents, 2 times 30 cubic meter, one lye, one acid. So there's a lot of water that is used in order to utilize the active carbon adjectives. We've looked at that and come to a solution, a new system that is actually only utilizing blue light as the source of breaking down the riboflavin into smaller molecules. While doing that, in the later process down the stream, the riboflavin that is left will not be contained inside the crystal. It will be on the outer sides of the surface of the crystals, and with that they can actually be cleaned off. So the powder coming out at the end will be as we like them to be, below the 2 ppm or in between. We can regulate it in between, so that what we want we can achieve. The system is a module-built system where liquid is coming in here, flowing through these segments here, and this is where it is radiated. So one turn through and it's coming out as the same place with liquid. In these areas here, you can see here, you will have the box that is exposing the liquid inside with blue light, the liquid. So here it is actually where the riboflavin is broken down. Over here, you can see 1 and 2 example here. It is white powders that has been exposed to the blue light. And number 3, you can see it's pale yellow. This is where it is not exposed and not treated without any blue light. So it's yellowish. And this is what the industry normally tend not to like. It is exposed to the blue light, so it's passing in tubes, it's passing the blue light, and here it is actually exposed and then it's broken down. There are some conditions that needs to be in place in order for the process to work at its optimum. One is turbidity, so how easy is it for the light to pass through the liquid? So the less turbidity it is, the better. Also, temperature has an influence, and that is why we would like to work in temperature ranges between 50 to 75, at best 70. And also we know that the case or the volume, the force that we are adding through the tubes is also important. So we want to have turbulent flow inside the machine, and with that you will have a good interchange of the liquid in front of the bulbs. So you will have a good impact of the light inside the liquid. That's why we want to have this turbulent flow. In the video here to the left hand side, you will see that there is we have introduced liquid inside the machine, and also a little bit of air. So you see bubbles, how they're actually circling around, just to demonstrate how this liquid is turbulent inside. And that is by purpose. The benefit of the blue light whitening system is that it has a very high product quality, so it can reach the threshold of the 2 ppm, so we can go down to 2 ppm of riboflavin left in the lactose powder. At the same time, we can also vary in between the 2 ppm up to no actually removal. And that is a benefit that the active carbon system has less ability to do. We reduce the environmental impact by less water and also less lye and acid, and we also eliminate the carbon cartridges that can have an impact on the end result, as it is black carbon in white powder. So if there are any carbon slipping through, then you will see that in the end product. It has a lower capex. We tend to say it's half the price of the carbon cartridges. It is reducing the overall OPEX. Energy of pumps and so forth that is forcing liquid through the carbon footprint is equal to the energy needed for the bulbs, but you will reduce the water and the acid and lime, and with that you will have a high benefit of utilizing the blue light system. It's a hygienic design because it's operating inside tubes at all time, and it only needs to be the CIP, so cleaned in place, while the rest of the upstream or downstream system is being cleaned. It's easy and economical to integrate into existing lactose processes, as it only needs to have blue hoses attached to the inlet and outlet, so we can bypass the active carbon, which is at your site, and then we can actually show proof by the rental unit that we have available that the level of removal from removal will be part of the KPIs that we can actually propose. It takes up a much smaller footprint, somewhere a quarter of what is needed for the active carbon footprint. Less maintenance. It is the bulbs that needs to be maintained, and they are actually designed to last for a year or more. The lead time, we are aiming at having around half a year as a lead time due to its modular construction. And as I said here, we have a rental unit available, and we are fabricating one more rental unit, which will be available at the start of next year. Please visit our homepage, spx.com, and then here you will be able to find a lot more information about this new development, this new technique that is available in the market. And all the technical aspects of this, how much amp, the size of the equipment, and so forth, you can find that on our homepage. Thank you for taking the time to listen to me about this, and now it's time for questions. Thank you for listening in. I think we have a couple of questions here. I will select one. That is carbon columns also are CIP'd during the regeneration mode. And the question is actually, so why is this not a hygienic design? It's true that the columns, they are CIP'd during regeneration mode. And it's also true that they are utilizing both lye and acid, but it's actually being performed in a plug flow. So that is quite difficult to actually accurate mix the liquid into the carbon, and this is where it's the process is that it's lifting the carbon in some mixing for a few seconds. So this mixing is really quite far from being really truly sanitary. So that's why we believe that we state that our design here is hygienic. It's inside tubes. So here we have the availability to do a full CIP of the unit and all the holding cells and so forth. So that is that's why we're stating that. Then there is another question here. Are there other steps in the lactose process which is influencing the level of riboflavin in the lactose powder? Yes, there are. First of all, the feed can vary over the year, so there will be seasonal changes in the milk coming in, but also the crystallization and the washing step has an impact on it. So that is why we would like, and we have developed this site rental unit where we can actually go out and demonstrate at the time of doing the test. We can actually go to the point of the desired level of riboflavin, so the target of the level of riboflavin we need. Then we have another point here. The video shows good turbulence.
But what if the hydraulic flow is low at the point of integration? Yeah, for the application, we have developed, let's say, an option if the hydraulic flow is low to get the desired turbulent flow in front of the glass where we have the bulbs showing or radiating into the lactose. So that can actually be done. So what we would like is to have high turbulence and low turbidity. But what if we have then also high turbidity? Then we will need to perhaps even go into recirculation mode over the blue light system. So that's also an option to get to the targeted amount of Riboflavin. Then we have a question here. Yeah, if the customer do not have a clarifier, where would you recommend to integrate the blue light? Yeah, if the process is precipitating the calcium out, but don't have a clarifier, then you still have a high turbidity, and then I would incorporate it into the heat and hold tank where we have 70 to 75 degrees C, and this would be quite efficient at that time, even with the turbidity being high. Alternatively, it could be also in the pasteurization step, just to the feed of the evaporator. This is also where you have a temperature around 75 degrees C, and this is also where you could actually incorporate it. So it's temperature that is very important, that we actually have the right temperature. This is why we stated that between 50 to 75 degrees C, that would be really the optimum conditions to have the blue light system working at. So hot and turbid, still okay. Cold and clear, not. So even if we are down at the, let's say, the very start of the process where you have a lot of flow, but you have only 13 degrees C, and it's very clear, so no turbidity, that is already tested as being we cannot do any real reduction down to the desired thresholds. Riboflavin is a vitamin, so why do customer wants to remove it in the lactose? Good question. Yeah, Riboflavin is yellow, and it's B2 vitamin, and it's the reason for removing this typically due to the color. For some applications, white lactose is preferred instead of yellow lactose. But again, as we also have stated, we can actually make, with this process, we can actually make a lot of settings within the running mode of the system. So we can choose to go all the way down by having max impact of the bulbs, so the blue light, into the liquid, or we can actually regulate that with reducing the not efficiency, but the effect of the bulbs into the blue light system. So with that, we can actually make different settings, different appearance, different levels of Riboflavin within the same process line. So today you could make 2 ppm with the right amount of bulbs or effect on the bulbs, and if you decide so, you could tomorrow you could produce 5 or 10 or whatever you actually desire. So there's a regulation mode within this new system. That I think covers also some of the other questions that we had here. Yeah. Do we have any other questions? Yeah, I think we have covered some of this, and there's a question if it works within other processes. We have developed this system, this system with blue light to actually gain the needed level of riboflavin coming out of lactose. We are scratching the surface here. We know that there will be a lot of new developments in new applications or other applications where color is something that we want to remove. We can change the color, the wavelengths of the color. We can change anything in that. But what is let's say the beauty of the system is that we can determine and we can test these new applications, and we have already had questions coming in around these new applications. So what we would like to do with new developments, new application, is to have it tested in our test center here in Søborg. We only need around 10 liter of a sample, and with that we have a lab scale, a tabletop model, where we can not prove totally, but at least make the first initial test of how would the liquid react to a specific wavelength, color, and so forth. Yeah, that's also, is it really needed to have a decalcification process included? No, it's not a must. We have been doing tests also with customers where they did not do decalcification. So the liquid gets less transparent, and this is why we then need to have a higher temperature and also a more turbulent flow in front of the cyclads, where we have the radiation of the blue light into the liquid. There's a balance there. So if it is really turbid, then there will need to be a high turbulence, so a lot of flow. And this is also why we have developed, or we are in process of making a testing module that can be sent out to site, where we have a smaller quantity of liquid going through. With that, we will be able to meet also other areas of the market expectations. Yeah, there's a question of vibration in the system. That's I would say it's close to none, as it is liquid that's flowing inside tubes, and it is circulated and then and being turbulent, but not violently turbulent, but it has to be circulating. So with that, you are circulating the liquid in front of the bulbs that is then getting the blue light into the liquid. So turning that, you will have a good impact of the and efficiency of the system. That do not generate any vibration, so it's actually a very silent piece of equipment. But inside the cabinet, there is a lot of blue light for the lactose process. Yeah. Yeah. What steps are taken to control the vibration? Yeah, we don't need to take any steps to control the vibrations, because there aren't any. It is put it on legs that is according to sanitary standards. So it is a module. You can move it around. So in cases where you don't have really space for doing the test, it's a matter of having the unit placed as close as possible, so that being somewhere around 30 to 50 meter maximum, and then connected with blue hoses to bypass the existing carbon cartridge active carbon system, and with that we can actually demonstrate the efficiency of the system. Yeah, there's a lot of questions coming around other applications, other usages of this unique system. And as I mentioned, we are scratching the surface now. We know that there is a lot of stuff where we, or let's say areas where we can chip in with this new development. And this is where it really gets interesting, because we are only opening now the box of all the different areas where we can actually perhaps give benefits into the market. I got a question here also around what about microorganisms? Well, the unit itself is CIP-able, so every part of it internally can be CIP'd together with the up or downstream process when that needs to be CIP'd. It is not it's visible light, so it's not the UV light that is utilized, so it will not kill germs inside the liquid. So it's not a water treatment equipment. And that is already in the market. This is where we can, make changes to the appearance of liquids formed into powders or whatever. So that's the view of and the beauty of this new system. What I perhaps missed to just also inform that when you utilize today's active carbon system, then there is a little bit of downsides here, because some of the crystals that not the crystals that are made with that traditional process has a certain particle size distribution, and if you want to turn that more yellow, not by measurement but by appearance, you can actually mill that down, and that also takes up energy. It is not part of what we have been looking at and justifying the system as such. We've just looked at as a pure switch from one process, active carbon, known today, into this new development blue light system. Yeah, I can see that we are coming to a closure here. So due to time, I would like to let you know that any questions that we did not get time to answer, please use the link in the posted chat section or after this webinar, and we promise to get back to you in due time. And I would like to thank you for the time for joining this webinar, allowing us to give you some insight of this very interesting new, very new system solution. And please also visit our homepage. There's a lot of information also there, technical information. I've not touched all the technical side of it, how many amps and so forth, but there's a lot of good stuff out there. So I wish you all a nice rest of the day. Thank you very much for listening in. Have a nice day. Bye-bye.